But here, instead of having total F for the whole magnetic core, how much is this F, total F, for each unit length in this magnetic core? So it's called intensity, meaning that it's like you are measuring how intense is the MMF in this magnetic core.
Yes.
Okay?
Doctor, when it reaches
Yep.
to the saturation, how B will behave in this relations? B equal mu H.
Well, if we reach the saturation, as I mentioned, B will be almost constant in relation to H. But in general, the assumption that mu is constant is not valid anymore if we have this BH curve or magnetization curve. So you cannot say, for example, is that I can use this equation assuming that mu is equal 100, for example. You cannot do this because this mu, it can be 100 in this region, but it can be, for example, 1 in this region or 10,000. Because again, this is the definition of nonlinear relation. Mu will be different in each region. So the question here is, if we cannot use this, what can we use? Well, this is a good point. You can use the drawing here, the figure, the relation, the curve between B and H. Because mu is not constant anymore, and it has different value for different combination between B and H. So if you would like, for example, to know what's the value of B at H is equal 100, you need to go to the curve and find what's the corresponding value of B. If you need to find what's the value of B at H is equal 1000, you need to go to the curve and find what's the corresponding value of B. How we can find the value of a mu at these 2 points?
It will be the slope.
الميل.
Yes, basically the slope, or B over H, this value B
Yes.
over this H. Is it gonna be the same as this value of B over this value of H?
لا.
No,
It is
لأنها مو
linear, yes.
linear.
because it's non-linear. So
Yes.
at each operating point, we have different value for mu and different combination between B and H. So we can use the curve, or we can use the table if we have a table representing the curve to find the relation between B and H. So this is important because if you remember, we had many equations before. For example, we have F is equal Ni. F is equal HLC. F is equal flux R. You remember this? We have also some equations like flux is equal BA. B is equal mu H. And yeah, this is what I remember.
B equal flux over A.
Yeah, which is the first one. Yeah, this one. Okay, so now we know that we cannot use this relation anymore. Okay? And we cannot use this relation also. Why?
It's for linear.
Not exactly, because this R is what?
Is LC over mu n.
And we just mentioned that mu is not constant. So to use this, you need to find the mu at certain operating points that you are dealing with. And after that, you find what is corresponding reluctance for that mu. And after that, you use it for this equation. So again, what's the conclusion here? Since mu is not constant, the reluctance also is not constant, right? Makes sense, because reluctance relies on mu. So don't take this for granted, this equation, unless you find the corresponding reluctance for your operating point. And after that, you can use this. So how we can solve the problems usually with this now BH curve? Well, it's easy. It's not complicated. Usually, you go from here to here, or from here to here, using BH curve. For example, I can give you N and I, and I ask you to find what is flux. Well, since you have N and I, you can find what is H. Then you find what is corresponding B from the BH curve, and after that, you find the flux. Or the opposite. So you always move from one side to another side through the BH curve. And we are going to see this in a couple of examples. Or you can find, once you find H and B, you can find what's the reluctance, and after that you can use this equation. It's up to you. Okay? So these are just few examples of different BH or magnetization curves for different materials. For example, the first one is for silicon sheet steel. And you can notice that the characteristic of this is a little bit sharp increase in the linear region. And after that, the saturation. The cast steel is in the middle between them. The cast iron is a little bit slower in terms of saturation. So how we can get all of these curves? Experiments, and we're gonna do something similar today in the experiment, or maybe you did it yesterday also if you had your experiment yesterday. So by doing experiments on materials, we can know the relation between B and H. This is just a figure to show mu R for a certain material. Mu R, which is the relative permeability, which we said that it's not going to be constant because of the nonlinear relation between B and H. And of course, we can calculate mu R by mu divided by mu naught. Or if we can substitute in this, we can find mu R also directly. And the mu R, you can see it here, it's not constant. Before we assumed it's just one value, but now we can see that it's changing when B and H change in the material.
Doctor,
Mhm.
we can observe from the graph that mu it's not constant at all.
Yes. Yeah, this is what we are saying. Yeah, it's not constant.
I mean, we said it's constant in some region before saturation, but
Yeah,
like,
that's true. That's true. But as I mentioned also here, not all the not all the materials are the same. For example, this one, the linear region is very narrow region, right? It means only for these H values and B values. But after that, it's highly nonlinear. Okay? So it depends basically how you take the samples here. But in general, it's nonlinear. So you might have different basically characteristics here. You might have something similar to this. You might have something, constant for a while and after that changing. It depends what's the relation. Okay? Just an example to know how to deal with this magnetization curve. Find the relative permeability of the typical ferromagnetic material whose magnetization curve is shown at H equal 50 and H is equal 1000. So we need to find the mu R. Okay. We need to find the mu R when H is equal 50. So mu R is equal B mu naught H. So at H is equal 50, how much the value of B? So that we can find what is mu R. So we go to the figure.
0.3.
Yeah, we go
Okay.
to the figure. It's an estimation. It's basically, this is 50 H. We just find the corresponding B for this, which is point, maybe 2.25 or less, 0.22, right? So if we calculate what is mu R, what will be the value here? So we divide 0.22 by 50 by 4 by 10 to the power minus 7. So the value here is 3,500. So if we do it also again for 1,000, what's the procedure? Same, B mu naught H, where H here is 1,000. What about B? Well, we go to the 1,000 and try to find the corresponding value for this, which is almost 1.5. So if we calculate mu R, it's going to be 1.5 divided by 1,000 divided by 4 by 10 to the power minus 7. This is 1,193. Because mu naught is the value of this, it's a constant, it's not changing. This is the air, right? So this is the permeability of the air, and we don't have magnetization curve for the air, we have only for materials. So the value of this is 4 pi 10 to the power minus 7. Okay, it's a constant. So what's the conclusion here? You can see that at a certain point, the mu R is 3,500. At another point, the mu R is 1,193. Okay?
Doctor,
Mm-hmm.
but in both cases we assumed, like, not assumed, like we take the procedure as we find the mu R in a linear curve. I guess we need to find like the power relation, then take the differential to find the mu accurately.
I didn't get completely the question, but BH basically representing the practical and experimental relation inside the core. And the mu is linked to this relation, as I mentioned before, because we know the relation between B and H is through permeability.
What I mean is the relation between B and H is like after some point it's a power relation, right?
Power relation?
Yeah, I mean from the the behavior of the curve, we can like assume it's a power by fitting the curve, or
You
what's
can
this?
you can okay, you can make assumption or simplification by fitting this curve to be like, I don't know, mathematical relation or mathematical equation.
Yes.
You can do that, but this will be simplification more than anything else. Yes, you can convert this practical curve to an equation. And you can say that B is equal, I don't know, 3 plus X, some 3H square or something. Anyway, mathematical relation. You can do this, but this is simplification. This is more precise using the BH curve. If you simplify more, you can find the equation. If you simplify more and more, you can assume it's linear relation, and that's it. Okay.
Okay.
So just a quick example here. A square magnetic core has a mean path length of 55 centimeter. So the length is 55 centimeter. Cross-sectional area 150 centimeter square. Number of turns 200. wrapped around one leg of the core. The core is made of material having magnetization K. So what do we know here is that the LC is 55, A is 150, N is 200, and it's a square magnetic core, one coil. So we are familiar with such magnetic core. How much current is required to produce 1.012 flux in the core? So we know the flux. We need to find what is the current. Before
we have flux and we have the area. We can.
Yeah, before let's discuss before. Before it was easy to find what is R, right? Which is LC mu A. Then since we have the flux, F is equal flux R, then I is equal F over N, right? As I mentioned, now we don't have this mu. And we know the mu is, we need to take it from the figure itself or the curve. So what should we do? Or what we can do? Since we have the flux and we have the area, what can we find?
B.
B. Yes. B now will be equal to flux over area, which is 0.012 divided by 150 10 to the power minus 4. What's the value of this?
0.8.
0.8, okay. So now since we got B, what we can do, we can use the BH curve to find what is H from this B.
110.
Yeah, so B is 0.8, so we go to 0.8 here. So almost here. So yeah, let's say 110. Okay, is it clear? So 110 for H. Then what?
Multiply it by the length, find F.
Find the mu.
Multiply
We
by
can, yes,
It
which is
equal
once we
H
have,
I of length.
once we have H now, we have the length. Sorry, معلش بس خلينا. Once we have H, we have the length, we can find F. F is equal H LC. And from F, we can find I. You get the idea here?
Yes.
What if someone would like actually to find the reluctance or the equivalent reluctance of this operating point? Well, okay, it's doable. To find the reluctance, you need to find first what's mu. You have B, you have H, and after that you can find the reluctance. And after that you go back to the whatever you know before, and you say that F is equal flux R. Of course, there is no point here of complicating things, but just to explain that even reluctance can be found at this point. But this reluctance will be for this specific value for H and B. The other remaining questions, we already answered them. What is the core's relative permeability at that current level? Well, once we have B and H, mu R will be equal to B mu naught H. What's the reluctance? Once you have mu R, you can find the reluctance. Okay? Any question regarding this? just quickly to go through this example, nothing new again. We are just repeating ourselves here. Magnetic core has a BH curve as shown, fringing coefficient of 1.25. It means 25% more on the air gap. How much current is needed to establish an air gap flux density of 0.64? Assume N is equal 110. So we know that the BG is given 0.64. So we have this. N is equal 100.
We can find H.
Yes. So we can find H for the air gap. How we
And
can
mu
find
as
H? How we can find H for the air gap?
H for the air gap
Forget about H. Can we find the flux in the air
shouldn't
gap?
be constant.
Flux. How we can find flux in the air gap?
Fringing coefficient multiplied by the area multiplied by the flux density.
Yes. We know that the flux density is 0.64. Area of the core is, we can calculate this.
1.25 times.
We can calculate this, right? Because this is the width and the depth is given here as 20. So this is 20 multiplied by 20, 10 to the power minus 4. Multiply by what?
1.0, 1.25.
1.25, the fringing coefficient. This will give us the flux. Okay? So this is the step number 1. Step number 2, the flux in the air gap will be the same as the flux in the core because it's one flux in the whole circuit. Do you agree? It's like current. Yeah, it's one flux in the whole circuit. I'm not going to solve the whole example, but I will explain the solution. So once we find the flux in the core, what we can do is what? Now we need to represent the whole circuit. How many reluctances we have?
We have three. Two.
That's correct. 3. Why? This is Ni.
Why?
This is for the air gap. This is for the C2. This is for C1. Where C1 will be the 3 legs here. C2 will be what? This one, because it's thinner. Air gap, of course, will be air gap here. Okay? So we know that the flux is, we already have the flux. Okay? We need to find what is the current. To do this, we need to find, of course, before it was easy because once we find RC1, RC2, RG, we just combine them, and after that we find what we knowing also what is the flux, we find what is the current. Easy, which is F is equal flux R. But we don't do this anymore. So the best way to do it is to find what is H at each reluctance. To find what is H at each reluctance, we need to find B at each reluctance. So this one, we know it, which is B. It's already given. Can we find what is the value here? BC2. Yes.
Flux over the area.
Flux over the area of 2. Can we find the flux, the B here? B1. But the area of C1, right? What's the area? What's the area of C2? Well, it's gonna be 20 multiplied by 20. What's the area of C1? 40 multiplied by 20. Then what? So this is the second step here. Then what? Well, third step, we need to find what is HC1, HC2, and HG. From where we got HC1?
From the graph.
Yes, from the plot here. Once we know what is the value B, we go to the plot to find what is the value of H. Let's do it like this. What about the value of BH2? Same thing from the plot. Once we know the value of BC2, we go to the plot here and to find the value of HC2. What about the value of the air gap? HG. Is it from the curve itself? Yes, that's correct. It's not from the curve because this curve is only for the material. For the air gap, we go to the equation, which is
B over mu.
B over mu, yes. Mu naught. That's it. Mhm. Okay. It is the same for the whole circuit. Yes, that's true. شوف تخيله مثل ما قلت انا من قبل، تخيله كانه الكتريك سيركت مع كرنت، او تخيله مثل ابياب مويه. انت لو عندك الحين شبكه مويه وهذه الابياب عريضه شوي اللي فوق وهذه شوي نحيفه، بس انت قاعد تضغط المويه تمشي كامل. كميه المويه اللي بتمشي في العريض هو نفس كميه المويه اللي تمشي في النحيف، صح ولا لا؟ نفس الفكره هنا. Okay. So after we find what is HC1, HC2, HG, what should be the next step? Well, it will be the last step actually here. We know that we have an equation which is F is equal HLC, right? Which is similar to KVL. So what we can do, we can say that Ni, which is this Ni, is equal HC1 LC1 plus HC2 LC2 plus HG LG, which is the KVL. You remember the KVL? Yeah, this is the KVL. What we are saying is that this voltage is summation of this voltage plus this plus this. This is basically what we are saying with this equation. And then how we can find N? We just divide current. Is it current? Current, yeah. How we can find the current? We just divide these values, summation of all of these values by N, which is 100. Again, we need to calculate it from here. It's the outer length. Oh, sorry, it's given. It's already given the length from here to be 170 centimeter. Similarly, here it's given 120. Here 170. So the average given directly here. Okay.
Victor,
Mhm.
there is another way of thinking. Can I use the reluctance equal LC over mu A? Then I do the summation of the reluctance.
Yeah, you can do this. Yes. Yeah. Once you find this H and you have B, you can find what is mu equivalent to B1 and C1. Sorry, B1 and H1. And after that, you find the reluctance for that.
Then I have to multiply it by the flux to find the total.
Yes, similar to what we did before. F is equal flux, equivalent reluctances.
Yes.
Okay. Same idea. So yeah, I will leave it to you. Just do it at home. Make sure that you do different approaches for this, just to know the differences. Try to do it with reluctances and try to do it with only H and B, as I explained here in this slide. And you have the solution here, as I explained, but the other one will be what? Will be using the reluctances to find the solution here. The current will be 52 amp. The last part is basically just discussing some losses in the magnetic circuit. And the main two losses, they are called in the core hysteresis losses and eddy current losses. And I'm gonna go through them one by one. Hysteresis losses, the meaning of this is that the relation between the current and also the magnetic flux is nonlinear. And again, we already explained this, if you remember. We said that BH, relation BH is nonlinear. So as a result, also the flux will be nonlinear with the current, because current is more linked to the H. Flux is more linked to B. So yes, if the relation between this and this nonlinear, so the relation between this and this also nonlinear. And since the current is AC, supplying the magnetic flux, we have the positive and negative cycles. There is the phenomenon, it's called the hysteresis loop in the magnetic core. And the meaning of this is, let's assume that we start supplying brand new magnetic core. So from zero, it's a new magnetic core. What will happen actually when we start to increase the current is that this magnetic flux will start to increase. Makes sense, right? When we go to the zero again, what will happen is that this actually will go, but not to zero. It still have some small value for the flux. And when we go actually to the minus, we go to the minus, then we go back, and etc. This is called hysteresis loop. And the actual meaning of this is that we have some residual. This is called residual flux. So it means that even if the current is zero, so if the current is zero, it means that supply is zero. You expect the flux to be zero, ideally. This is not true. There is still some residual inside the magnetic core. في باقي يصير flux موجود في الكور نفسه حتى لو الكرنت رجع للزيرو. So this is a magnetic flux that is stored inside the magnetic core. And it is considered to be losses because you lose part of the input because of this phenomena. And the amount of losses is basically, it's like an estimation of the area inside the curve. So if you can estimate what's the area inside the curve, this will be the amount of magnetic flux you lose because of this phenomenon. And this is called the hysteresis losses or hysteresis loop. And this basically phenomena is different again from one material to another material. Some materials, they store more magnetic field. Other materials, they store less magnetic field. If we have a material that it is storing less magnetic field, this is good for machines. This is called soft material. Okay? And it's good. Why? Because you don't want machines to store magnetic field and lose part of the input or the output. So you try when you design the machine to pick a material that it doesn't store magnetic field. If we have hard material, meaning that we have more magnetic field to be stored, this is good for permanent magnets. Permanent magnets, where basically we use in certain applications, this is considered to be hard material, where the magnetic field is stored inside the magnet. How we can calculate, as I mentioned, this type of losses? Well, either we estimate the area under the curve here, or there is a mathematical equation that can estimate the amount of losses. And this is the mathematical equation. It is relating the constant with the volume of the material, with the frequency of the supply, and with what's called the maximum flux density. This maximum flux density is also linked to a value n, which is a constant, again, ranging between 1.5 to 2.5. So the equation is like this: constant, frequency, density. So the amount of losses you have here is linked to the frequency. So more frequency of the AC supply is higher hysteresis losses inside the machine. So if you supply the same material with current with a frequency of 60 or current with a frequency of 50, you would expect the frequency of 60 to give more losses in the magnetic core. Of course, the difference is very small, but the concept is that with higher frequency, we expect higher hysteresis losses. I'm going to speed up to finish this part. I just have a couple of slides. The other type of losses is called the eddy current losses. The eddy current, the concept is also simple. Why? Because the magnetic material that we use for magnetic circuits, it's not completely insulated material from electrical point of view. It can be also conducting material, meaning it can conduct both magnetic field and also electricity. Iron, for example, is a good conductor for magnetic field, but it also can conduct electrical current. So what is the problem here? No problem. But if you have magnetic field inside the magnetic core, and if you remember the Faraday's law, which is basically if you have magnetic field and a conductor, current or voltage will start to induce, right? So this is what's happening actually inside the magnetic core. We have magnetic field in this cross-sectional area. Because we have magnetic field and also conductor, voltage will start to induce inside the magnetic core. Is that a problem? Not yet. Because also we have conductor, of course we have resistivity for this conductor. So it's not only reluctance, but also resistance. So if we have voltage and also we have R for this material, what will happen? Current now will start to be resulted inside the core. So current will start to flow inside the magnetic core itself. So current with a resistor now, yes, we have losses. And now the core will start to heat up because of the current flowing inside the core itself. And this is called the eddy currents. And we can estimate also this current similar to the previous one using the equation. K constant, now F square, frequency squared, and also the density. So how we can resolve this issue? I mean, is there a solution for this? Well, yes, there is a solution. What's the solution? What do you think? We cannot prevent the voltage to be induced, but we can prevent this. We can break this. We can make this very high resistance. Okay? If we make the resistance very high, even if we have induced voltage, the amount of current will be very small or negligible. So the question now is how we can make this R very high. We use the concept of lamination, meaning that instead of using one magnetic core, one piece of material, we just break it down into sheets, very small sheets. And if you open a small transformer, you will see these small sheets of materials. So why this actually might increase the resistance? Because remember, resistance is equal to L, resistivity, area. You remember this? So basically, if you make the core sheets, from resistive point of view, you are playing with this area. You are making the area very, very small, and the resistivity now will be very high. From the magnetic point of view, you are not playing with this area because it's not affected by the physical separation between the sheets. So yes, we make the core laminated, meaning sheets, to increase the resistivity of the material such that we decrease the eddy current losses. The last type of losses. I already explained this before. It's called the leakage flux, which is basically the flux that we lose from the core to the surrounding air, because we have the reluctance of the core, we have reluctance of the air. So small percentage of the flux will go to the air, which considered to be losses, because you want to utilize all the flux inside the core. Is there a solution for this? Yes, there is a solution. What we can do, and also you can notice this if you open any transformer, we can isolate the core from the air. We usually use like special insulation, like the paper sheets. If we put isolation around the core, that's it. Nothing actually will move from the core to the air. So this is the end of the magnetic circuit. If you have any question, you can ask me, because we have office hour in the coming 40 minutes. Otherwise, I will see you inshallah on Wednesday. Allah يعافيك.